This is section 17.4, Green's theorem. Green's theorem is one of the three huge accomplishments at the end of all of calculus. We get Green's theorem, Stokes' theorem, and the divergence theorem. I'm not sure yet if I'm going to show you the proofs of all three of these theorems, but they're the big, massive, achievements of vector calculus. So I'll at least show you the proof of Green's theorem this time. The goal here is to first just be able to state and read what Green's theorem says. Then we'll use it to compute line integrals, and then we'll actually also be able to use it to find areas. So what is Green's theorem about? And then I'll show you the proof, a proof. So Green's theorem connects the circulation of a vector field. So we've got a vector field. We're going to be in the plane. So I'll say that the vector field is made of two components. Capital M is a function of xy, and capital N is a function of xy. The picture in your head of this vector field should be that at each point there's a vector. And here I'm setting up my vector field so that the way that it works, if we go around this loop, the vector field will help us go around the loop. So this loop is a curve C. When you have a vector field and a closed loop, you can compute the circulation of the vector field around the closed loop. And that's just the work done as you go around the loop. So it's the line integral around the curve C, it's a closed curve, of f dot dr. So this is the circulation. The key thing that Green's theorem does is it connects the circulation, the amount of work that the vector field does by going around the loop, with the stuff that's going on inside the loop. So if the circulation is not zero, then the key insight is if there's swirling going around, if the arrows are helping us as we go around the curve C, then when you look inside the curve C, you should notice kind of a swirling action. And that swirling action has a name. It's called the curl, but we're not defining the curl yet, so I have to call it the swirling action. But basically, if you go in a loop and the wind helps you, then that means you kind of walked around a tornado. Maybe a small tornado. Okay, so how does Green's theorem actually go when you write it down? Green's theorem tells you that the integral, the circulation, this work integral, actually equals an integral that you do on the inside of the region. We'll call the region R. So a line integral will equal a double integral on the region inside the curve. Okay, what actually is it? Well, it will end up being, now I'm worried I have the order backwards, but I think it's partial n partial x minus partial m partial y dA. Let me make sure that I have the order right. When we're not actually doing curl, it's really hard for me to get the order correct. Okay, we got it right. This we have this line integral. We have a physical understanding of what it means. We are dotting two vectors. Dotting two vectors comes out with a big number if the vectors are pointing the same way. So we're going around the loop, the curve C, and we're trying to see if the vector field points the same way as our curve. So this is the circulation. It tells you how much the vector field helps us as we go around this path. This thing, we have no intuitive understanding of what it is at all yet. Later, we'll know that this is called the curl. This equation, if this turns out to be true, which it is, it's called Green's theorem, this gives us an understanding of what this means, that this quantity is the swirliness on the inside of the region. If you add up all the swirliness, it will turn out that you get the circulation. The really weird thing, though, is that you add up the swirliness on the inside of the region, and you get a result that tells you what's happening on the outside of the region. This is a super important fact, and this quantity seems to come out of absolute nowhere, so I want to carefully prove that this is actually true. This is definitely the longest proof that we've done so far in the class. It'll come in two parts. but it's such an important fact that I want to show you how all the stuff we've done kind of like links together and lets us see that this is actually true and that there's no magic going on behind this equation. Okay, so the first thing we'll do is we'll notice that, like, I'll just try to calculate this double integral, but I'll notice that since the double integral has two parts, we can do the two parts separately. So first we'll consider just the integral of partial n partial x dA on this region. And what I'll do is I will assume that my region is like a reasonable shape. All the different proofs of Green's theorem that you find in various classes or in various textbooks, they always assume that the region is like somewhat reasonably shaped. The proof that I do, it will only work for regions that have a top function and a bottom function, and also have a left function and a right function. So it's going to be a vertically simple region and a horizontally simple region. It turns out that the theorem is true in much wider like situations than that, but yeah, we're just going to do it for a region that looks like this. My curve C is going to go this way, counterclockwise, and I'll say that there's a bunch of different parts of the curve. So this part of the curve, I'm going to call y1, the bottom half of the curve. And this part of the curve up here, I'll call y2. We'll end up also needing to name the left and right sides of the curve. So this part of the curve, it's labeled x1, the left half, and the right half of the curve is labeled x2. Similarly, because we've assumed that this is like horizontally simple and vertically simple, I'll say that this x2 part of the graph is given by this function x equals x2 of y, and the left part is given by x equals x1 of y. It's just going to make it possible for us to actually see like where this stuff comes from. So let's just go. I'm going to try to do this part of the integral, and this will be half of the swirly side of the integral. Okay, so let's do the integral. If you're doing a double integral, you get to decide whether dA is dx dy or dy dx. And because we're taking an integral of an x derivative, I kind of want to do the x integral first. So I'll let dA be dx dy. Now, once you make this decision, what it does is it decides the bounds of your integral. So the outermost bounds are numbers. The y bounds are going to go from, on our picture, c to d. And the x bounds go from the left function to the right function. So this is x1 of y to x2 of y. Now that we've set this up this way, I can do the innermost integral even without having a formula for n, because I have the integral of dn partial n partial x dx. So the integral and the derivative undo each other. And just like for all double integrals we've ever done, the outermost integral just sits there and waits for us, and the innermost integral we can actually do. So I get n. N of xy from x1 to x2. Now, what are these bounds? These are the x bounds, so I plug them into x. So I have n of x2 of y, comma y. Notice that I just put the x2 in for x, minus n of x1 of y, comma y. And this is all dy. Okay. What is this? Like, who cares? This is like a huge, ridiculous object. Like, why would we deal with this ever? And the answer is that this line integral of c of f dot dr, it actually has a component that kind of looks like this. If you write down what f equals, I'm like in the way of the thing I'm writing. If you write down what f is mn, and the differential form of dr was to write it as dx dy. So we're looking for m dx, and we're looking for n dy. And so when I got all these n's and they're all dy, I start to realize, oh, interesting. I may actually have like part of the answer here. So let's see if we actually have the right part of the answer. I was hoping that I would have the integral around the entire curve C, but it doesn't look like I do. Instead, I'm just going from y equals c to y equals d. So what am I doing here? Well, let's split this up into two pieces. So I'll have the x2 piece and the x1 piece. And I go, what is happening here? So this is the integral of n dy, but what path are we actually taking here? Well, the path we're taking is the path where y goes from c to d, and x is on the function x2 of y. So this part of the, this integral is the integral of n dy, but it's on this part of the path, where y goes from c to d, and x is on this function x2. So this is the integral over the curve x2, like the capital X2, this part of the curve, the right half of the curve of n dy. Now I have a minus. This is a little weird. So what is this thing? This is also y goes from c to d, but x is on x1. So this integral starts here and ends here and follows x equals x1. And you might say, oh, well, it seems like this is the integral over x1 of n dy. But it's not. x1 goes the other way. x1 is part of this curve C. And so this part of this integral is actually the opposite of the integral of n dy. So it's actually minus the integral. So this is crazy. The minus minus cancels, and I just get the integral of n dy over x1 and x2. Well, x1 and x2 together, that's C. So I started with half of, so here's Green's theorem up here. I just attacked the first half of Green's theorem, and when I attacked the first half of the integral on the right side, what I got was the second half of the integral on the left side. If I do it again with the other half, and I get like the missing half, then I'll be done and I'll prove that these two are actually equal. So the double integral of partial n partial x dA came out to being the integral of n dy from the left side. Let's get a fresh copy of this, and I'll try to do minus partial m partial y. So now we're considering the integral of minus partial m partial y dA. I'm hoping that this equals the thing that we were missing from before was, I guess it was m dx. Because we found n dy. The n dy part was the partial n partial x part. Okay, let's see if we can make it happen. This one is, like this function, has a y partial derivative that just got taken. So since I'm doing the double integral, I get to decide the order that we're doing the integrals. This time I'll choose dy dx instead of dx dy like I did last time. This minus better like be important and helpful, otherwise I'm going to be really disappointed. Okay, the outermost bounds are the x bounds, so x goes from a to b. And the y bounds are functions, the bottom function and the top function. So we're going to have y1 of x up to y2 of x. Then we do the innermost integral again, just like we did last time, and the outer integral sits there and waits. I'm going to have just m of xy from y1 of x to y2 of x. These things are the y bounds, so I'm going to plug them in for y. So I'll have, leave the x alone, plug y2 in for y. Oh dear, minus. Let's keep the minus. The minus has to save us here. So plug this y2 in for y, and then subtract. So this one will actually be plus. I again have two pieces, and one of them is negative for some reason, so let's split it up again and see if we can figure out what's going on. So I have minus the integral from a to b of m of x y2 of x dx plus the integral from a to b of m of x y1 of x dx. Now, what is this thing? Well, we were hoping to find m dx, and in fact here it is, m dx and m dx, just like we wanted, but I want to make sure that I'm actually doing the curve c, and my bounds here are from a to b and from a to b. So let's see what's going on. This one says start at x equals a and go to x equals b and follow the curve y2 of x. That's this way. Is that the curve y2? No, that's the opposite way of the curve y2. So this integral is actually minus the integral over y2 of m dx. I have this extra minus sign floating here, and it's very helpful because it will let me cancel out the minus sign that came from me going the wrong way. Then I look at this one, and I say, okay, well, this one starts at x equals a and ends at x equals b, and it follows the curve y1. And that's actually going the correct way. So this is just the integral over y1 of m dx. This minus sign saved me, and I have plus for both. So this is the integral of m dx over the entire curve that follows both y1 and y2, and that's called c. The conclusion here is that when I look back at what Green's theorem actually said, Green's theorem said that I had this line integral equaling this double integral. But the line integral is in two pieces, m dx and n dy. And the double integral is in two pieces, the one that had the n and the one that had the m. We took the two pieces and showed that one piece equaled the other, and that the other half equaled the other half. So combined, these two actually equal each other, and that proves Green's theorem. So what's the summary? The summary is that the m dx part equaled the part that had the m. And the n dy part equaled the part that had the n. So when you add together both sides of this equation, the left side adds up to the left side of Green's theorem, and the right side adds up to the right side of Green's theorem. It's kind of awesome. Okay. Maybe you don't care about proofs of theorems, but this is a huge important theorem, and the fact that we know how to do double integrals and do them like either dx dy or dy dx, that's the only advance you need to actually prove Green's theorem, which is this huge, powerful fact. So hopefully you feel like your time wasn't wasted. Yeah. So let's just get it in a box. This is Green's theorem, and this is the circulation form of Green's theorem. It says, if you have a simply connected region with a piecewise smooth boundary, so no weird, well, you can have corners, but you can't have like tons of corners, and you go around counterclockwise, so that means that like you always walk such that the inside of the curve is on the left. This mattered while we were doing the proof. If the arrows had been the other way, we would have had to switch everything around. So if you're doing that, and your function is fg, okay, I had called it mn, but whatever, then the circulation around the curve equals, well, this is how you split up the circulation around the curve. It ends up equaling this thing, which is the curl of the vector field, when you integrate it over the region on the inside. Okay. Sorry, I'm just like really excited. So what does it look like when we draw a picture of it? Well, what it looks like is if you follow some curve, C, the vector field either helps you or hurts you, and you can tell whether the vector field helps you or hurts you by looking inside the curve, in the region on the inside, and adding up this quantity, which tells you how swirly the vector field is on the inside of the region. The fact that those two are equal is like pretty surprising, but the proof is what you just saw. Okay, one more note is what if you had partial g partial x equals partial f partial y? Then you would have the integral of f dot dr. I'm just going to write down Green's theorem here first. And I can never remember the right order, but it looks like I'm getting it right on the first guess every time. So here's Green's theorem. If partial g partial x equaled partial f partial y, then these would cancel, and you would get 0. So if these are equal to each other, then the circulation is always 0. That means that the vector field is conservative. So, yeah, I mean, that's what we did in the previous section. So in a way, what you can imagine this quantity as being, you can imagine this quantity measuring how not conservative the vector field is. If the vector field is conservative, then these two objects are equal to each other all the time. If the vector field is not conservative, then it's possible for the vector field to help you when you go in a loop. And this thing is the measurement of how far away from conservative your vector field is. That measurement, how not conservative is your vector field, is called the curl. This is the two-dimensional curl. We'll have the three-dimensional curl here in a minute. It's just this quantity. If the curl is 0, then the vector field is conservative. Okay, so let's actually use Green's theorem a couple times. I feel like some theorems are useful some theorems are good because you can use them to solve problems. Other theorems are good because they're crazy and they don't seem like they should be true, and it's just like awesome. And Green's theorem is getting close to the awesome side of things, so I almost think it's a letdown to use it to calculate examples. Many of you are going to be engineers, so you're like, please just show me how to use it, and that's fine. Okay, so let's use the Green's theorem to get out of computing a line integral. So I have some vector field. The vector field, you should imagine, is just filling the plane with arrows. Some of the arrows help us when we walk down a path, and some of them work against us. This is a force field. This should be your example in your head. C is this path where we're going to walk counterclockwise up this parabola and back down this line segment. If the vector field is not conservative, then it's possible that the vector field will either be circulating to help us or circulating to oppose us. You could do the line integral. We learned how to do line integrals directly. You parameterize the path. The path will be called r, or the parameterization of the path will be called r, and you just drop everything in here and do the integral. But it can sometimes be really complicated. Green's theorem says, nah, whatever, don't worry about that. Instead of worrying about what happens on the outside of your region, instead look at the inside of the region. And do a double integral instead. And I think your reaction here should be like, what? No, I would rather do a single integral than a double integral. But no. The double integral is going to be much easier because you don't have to parameterize the paths. And the path parameterization is the whole work of the line integral. Instead, you get to do the double integral of this quantity. This is the curl. I wish I could feel confident about the order that I've written this, but I did get it again. Okay. What are these f and g? This thing is little f, and this thing is little g. So let's do it. Partial g partial x is 2x plus 2y. Partial f partial y is 2y. Notice that taking the derivatives of these polynomials smashes them down and makes them much simpler. So instead of having to parameterize two paths and dot them with this crazy vector and then do all the integrals, instead I'm just integrating 2x on this region. Well, how do I do a double integral over a region? Well, I have to figure out how to get the bounds into the, get the region into the bounds of the integral. Since these both are functions y equals a function of x, like this is y equals 2x, and this is y equals, does it say? Just y equals x squared. Since I have functions y as a function of x, it's going to be easiest for me to put those functions as the bottom function and the top function. So I'll have dy dx. So I'll let dA equal dy dx. That's my order that I'll choose. The y bounds are the bottom function and the top function. The x bounds are the lowest number x and the highest number x, which is 0 to 2. So let's do this integral. The outermost integral will just sit there and wait for us. The inner integral is a y integral. So this is the integral of a constant, dy. So I just get 2xy from y equals x squared to y equals 2x. Plug in 2x for y, and I get 4x squared. Plug in x squared for y, and I get 2x cubed. Finally, I can just do this integral. So I get 4/3 x cubed minus half x to the 4th, all from 0 to 2. Plug in 2, and I get 4 times 8 over 3 minus 16 over 2. And this is 8/3. So the line integral, which was the amount of work that the vector field does as we go around this loop, came out to a positive number. That means that the vector field actually helps us when we take this path. Cool. Let's see, I want to see a picture of this vector field like generated by a computer before we move on. So what is the vector field? It's y squared in the x component. And x squared plus 2xy. Switch the view here. I'm in field play again, which we've looked at a couple times, but it's Anvaka field play, which is what you can search for. So we're starting here at the origin. And then the path that we followed was we followed a parabolic path and came back along a line segment. The parabolic path, the vector field was helping us, for sure, and the line segment coming back, the vector field was working against us. But what the integral does is it adds up the contributions so that you can figure out what the total contribution is. This vector field isn't conservative, so we got something that wasn't 0. And yeah, I don't know. Using Green's theorem made it much, much easier. I wonder if I can get just the correct bounds. So 0 to 2 and 0 to 4. Oh, it won't make it a non-square region. Looks like things are real serious along this line. Yeah, I don't think I can get the path to be drawn on here. That's okay. Okay, so that's how we use Green's theorem to compute a line integral. You get out of doing the line integral by instead doing a double integral of the curl, which sounds harder, but is actually easier. Okay, let's do another one. Now we're following this crazy loop where we follow these half circles. And the line integral is something completely insane. where the vector field is, so this thing is f.dr, where f is these parts, and the dr is this dx dy. This, when you see this sum of like something dx plus something dy, you should imagine that that came from the dot product of something with dr, and that something is the f. So we're finding the integral around a closed curve of f dot dr. You shouldn't try to do this by parametrizing this path, because this path is insane. The path, like, it's got a line segment and then a half circle and then another line segment and then another half circle going the other way. So you'd have to do 4 line integrals to find this. Green's theorem says, don't worry about it, just consider the interior of your path, what you walked around, and call it r. Then Green's theorem tells you that this circulation integral of f dot dr is actually equal to the double integral over that region of the curl of f. Oh dear, not partial f. This is g, and this is f. So it's partial g partial x minus partial f partial y dA. This is the curl. Okay, let's just find it. I can find partial g partial x. Partial g partial x is 2x. And partial f partial y, that's 2y. So we're finding the integral of 2x minus 2y dA. What you should notice is that the sine y, which looked like a complicated part of the problem, is gone. And the reason we know that that's just gone is that somehow it won't contribute to like the swirliness. It didn't appear in the curl, so its contributions along our closed path will all cancel out. That's super strong. Okay, now we have to try to actually do this integral. The problem is I don't really want dA to be dx dy or dy dx because the region is made of circles. So I will instead use polar coordinates. dA is r dr d theta. What are the bounds? Well, it looks like I've got a half circle here, which is r equals 1, and another half circle out here, which is at r equals 5. So r is going to go from 1 to 5, and theta doesn't go all the way around, it just goes from 0 to pi. So my theta bounds are 0 to pi, my r bounds are 1 to 5, and I'm integrating 2x minus 2y, but dA equals r dr d theta. Now, this is a common place for students to get stuck because you've got too many variables going on and you're trying to keep too much in your head at the same time. But you don't have to actually look at this and understand everything about it all at once. Instead, you should say, I'm trying to do the inner integral. It's an r integral. What are these x's and y's doing here? I don't want those. Once you notice that, then you can go, oh right, in polar coordinates, x is r cosine theta, and y is r sine theta. And substitute those in. This 2 is... Do you think the 2 is going to be helpful or hurtful? I can't tell. So anyway, this is going to be 2r cosine theta minus 2r sine theta, all times r dr d theta. To do the r integral now, I don't want to do it by parts. I'll just distribute the r in. Or maybe just like factor the r's out? It looks like I'll be able to just separate out the r's and the thetas entirely. Like if I factor out 2r, I'll get 2r times r. And then I'll have this, the theta part, which has no r's in it. So from the perspective of the r integral, that part is a constant. So it's just going to sit there and wait for the theta integral. Then I can do the r integral part, get 2/3 r cubed, and r goes from 1 to 5. So when I plug this in, I'll have 125 minus 1, which is 124. And 124 is not divisible by 3, so I just have some ridiculous number here. (248/3), I guess. Now I have to do the theta part of the integral. No problem. Integral of cosine theta d theta is sine theta. Integral of minus sine theta d theta is cosine theta. And then I've got this weird 248/3 that's just chilling, waiting for the problem to be done. When I plug 0 and pi into sine theta, you get 0 both times. When I plug 0 and pi into cosine theta, actually something happens. So I'm going to get, there's a 248/3. Then I need cosine pi, that's minus 1, minus cosine 0, which is 1. So I have to double this one more time. My final answer looks like it's going to be minus 496/3. So apparently, as I go around this loop, it's kind of like a weird shaped loop because it's made of semicircles and line segments and everything. This vector field, it's not conservative, so it doesn't all cancel out. Instead, this vector field hurts my efforts as I go around the loop. Do I have any reasonable way to check this answer? It's like a little bit of a crazy answer. I don't think I do. Oh well, sorry. Anyway, that's it. Let's actually cut the video here and we'll start doing the flux form and the second half of the 17.4 video.